Okay, let's get started then. Welcome to the third week of our deep learning course. And today we're going to talk about our first actual neural network, which is called Multilayer Perceptron. It's likely that some of you have seen this before. But again, it's important to review these concepts because this is going to be the basis for all the other networks we're going to look at in this course. So before, as usual, some logistics. The first programming assignment is out, and I know some of you already even finished it, which is good. But you have until the 30th to finish this assignment, if I'm not wrong. And there's actually a holiday next week. Originally in the calendar, I thought that the holiday would be the next month, not this month. So I think this upcoming Monday is a holiday, so we won't have class. Okay. Which happens to also to be the deadline, I guess, for the programming assignment. So just keep that in mind. All right. And last lecture we talked about linear regression with multiple variables. Then we saw the importance of vectorization, this idea of using special instructions in your CPU and GPU to speed up your machine learning code. And we then finished talking about logistic regression, and that included the sigmoid or logistic function, the binary cross-entropy loss, and at the very end we talked about how to adjust gradient descent or how to train logistic regression with gradient descent, which happens to be very similar to the linear regression algorithm because it turns out the gradients for logistic regression are the same as in linear regression, even though these are different models with two different loss functions. Any questions or comments before we start? Okay. So for today, we're going to talk about linearly separable problems, which is the kind of problems we have been dealing with up to now. And there's one algorithm I want to quickly introduce, which is the Perceptron. It has a very important it's very important historically, even though we won't spend much time talking about it because it uses a training procedure that is different than gradient descent. It's similar, but different. And I don't want to spend too much time talking about it. But, and I can give you references if you want, but the Perceptron is kind of like the basis of neural networks as a whole. But we normally now start talking about logistic regression and linear regression because these are actually models that are trained or can be trained with gradient descent. So it kind of like fits better the beginning of a deep learning course, at least in my opinion. But anyways, it's important to know that the Perceptron exists. And what is the difference between the Perceptron and, for example, logistic regression or linear regression? It's also a linear model. But then we're going to generalize these linear models in a framework or in a structure called a neuron that we're going to use from now on. And then I'm going to motivate the idea of multi-layer perceptron, discussing non-linearly separable problems. Then we're going to move on to discuss what the actual multi-layer perceptron is and how to get the inputs now with this neural network structure, and particularly also how to vectorize that calculation so we can do this faster. We're going to discuss different activation functions we can use with these networks, and finally how to deal with multi-class classification algorithms. And then for that we're going to need a variation of cross-entropy loss, which is categorical cross-entropy. So Up to now, we've been talking about linearly separable problems. Last class, we actually used this idea of tumor classification. And here on on your left-hand side, we have a one-dimensional version of that problem where our input feature is one value, the tumor size in centimeters. And then we want to predict a binary class, which is either 0 or 1. And 0 in this case means benign tumor, and 1 means a malignant tumor. And just for visualization and to kind of have a better understanding of how these problems generalize, on your right-hand side, there is the same problem, or is a plot of the same problem, but now we have two input features. Tumor size on the y-axis and patient age in years on the x-axis. And now the labels are still the same, right? But they are actually represented as simply by their colors. Okay? Or if you will, you could imagine a z-axis, right? That would be either 0 or 1 for these examples. But in both cases, these problems are linearly separable, which means there is a line that splits the data points into 0 or 1, or negative, positive examples, okay? And if your problem looks like this, you can use linear models to solve them. Like we can use actually, for example, logistic regression here. And in both cases, it would find this line that we actually call, if you remember from last lecture, we call this line the decision boundary of the model, which is the line that separates one class to the other. And remember that even though logistic regression uses the logistic function, which is not nonlinear, it has a decision boundary that is linear. So I want to introduce a new algorithm that's very simple because you already studied these ideas before. But the Perceptron, which was historically the first trainable neuron, is very similar, if you think about it, to logistic regression. It also wants to find a line that separates the space. So its hypothesis space, it's also the space of linear functions. Okay? So I have as input an x, which is a vector. In this case, we have 2 dimensions. We have patient age and tumor size. Okay? And I want to find the w, or a weight vector, that gives me a line that separates this space of data points with minimum loss. So the idea is essentially the same. And we're going to have this, we're going to try to find a line here. But now I wanted to visualize this more using more like a linear algebra lens here. Now, if you remember from the definitions of hyperplanes or planes in linear algebra, we can define a line in this case by using this w vector, which is orthogonal to the line, right? And the w vector here can be seen as a parameter that tweaks the orientation of the line. And the b vector here, or the b value, it's a scalar that shifts this line on the x-axis. Okay. So the perceptron is formally defined like this. It's very similar to the logistic regression in the sense that it applies a function to a linear combination of the weights and the inputs. But the function we use now is the sine function, or not sine, I'm not talking about the trigonometric function. It's sine in the sense of the numerical sign. So in this sine function, you would have this function to return +1 if z is equal or greater than 0, and -1 if z is less than 0. Okay, so basically it takes a number, a real number, and maps it either to +1 or -1. Okay, and the way you can interpret this is, if your z value is greater or equal, it's greater than 0, it means any point that is above the line. And this function is going to return -1 for any point that is below the line. Okay. So that's the idea. And it's going to return 0, exactly 0, if the point lies on the line itself or in the line. Okay, so any point that is perfectly in this line, this function signal is going to return 0. Okay. So here's an example of a learned model. Consider these W vector or weight vector minus 0.7 and 1 and the bias term 25. Okay? The way you run this model or you do inference with this model is like this. So let's consider this example now x1 50 10, which is kind of here, right? X is patient age, so it's a patient with about 50 years old, and 10 is a tumor size of 10 centimeters. I actually put a different number here. Okay, so this would be 51 and 8. So I think this is the point I was meaning to write here. So x1 would be 51 and 8. So if you do W plus X, remember this is the dot product between W and X, you would get minus 0.7 times 51 plus 1 times 8 plus 25, which is the bias term. That would give us the signal of minus 2.7, and that would be minus 1. Okay, so minus 1 means that this point, again, I'm talking about this point here, is below the line. So the model returns a correct prediction of minus 1. And if you try a different example now with x2 equals to 10 and 30, this would be a younger patient, right, 10 years old, would be even before here, right? It would be on the left-hand side of the y-axis. It would be a point somewhere around here, 10 and, no, tumor size right here. So you might have a very large tumor, but if you're young, that might be a benign tumor, right? This should be x2. But then if you apply the same model, again, minus 0.7 times 10 plus 1 times 30, which is the dot product between X and W, plus 25. Okay. That will give you the signal of 48, which is 1, which is also a correct prediction, because that's above the line. Okay. So that's the perceptron algorithm. Again, its hypothesis space is the space of linear functions, but instead of using the logistic function to decide a probability of that point being of the positive class, now it actually uses this more linear algebra formulation where you have this W vector and you want to decide if a certain point is above that line or below that line, okay? And because of this formulation, we actually cannot train the perceptron with gradient descent because this SGN function here is non-differentiable, okay? So you cannot compute the gradient here because it's not defined. So instead they had a very simple update rule that was pretty much it processes every data point, and using linear algebra, it tries to do a vector operations with this W vector to adjust the line to fit the points. It's a more geometrical idea. So you try to you process this point, and then you calculate the difference between your prediction and the actual label, and then you subtract these vectors, and then your line is going to be more oriented towards that to actually predict that point correctly. And if you do that for the entire data set, you can prove that this algorithm is going to converge to find the optimal line. Or a line that, not an optimal line, sorry, the line that actually separates the space. If that line exists, Perceptron is going to find that line, and you can prove that. But if it doesn't exist, then it's going to run forever, actually. You're going to end up being in an infinite loop. Obviously, then you can stop after a certain number of iterations. But it's a very interesting idea. And I wanted to show this. So now you're aware of this algorithm, that it exists. And now we actually know 3 different algorithms: the perceptron, linear regression, and logistic regression. And linear regression is used for regression, and the perceptron and logistic regression are used both for binary classification. Okay. So again, the perceptron is a binary classification algorithm. Now I want to introduce this idea of a neuron, which we can define as a computational unit composed of 2 parts: a linear combination of inputs x and weights w, right, that we're going to call z, and we're going to feed that combination to a typically nonlinear activation function g. And visually we can see a neuron this way. Normally draw it as a circle. And then we also normally draw the inputs independently, even though they form a vector, okay? So you have one vector as input here with d dimensions. But typically in a neuron diagram, you're going to draw it, all the inputs independently. But this, you can see these inputs as just one vector x, okay, with d dimensions. And so the first part of the neuron is a linear combination of inputs and weights, as I mentioned. That's going to produce a z value, which is a real number. And then that number is going to be used in a second part of the neuron, which is called the activation function. I'm going to use the letter g here to call this, to name this function. So then this g of z is going to compute our actual output, which normally we're going to call y hat. Okay. And that's our kind of the architecture of the neuron, or the anatomy of the neuron, if you want. And here's an example how we could fit this idea of neuron to our linear model so far. So if you get that neuron and change the z to a identity function, g of z equal to z, you get linear regression. If you change that g function to be the logistic function, then you're going to get logistic regression. And if that g function is that signal function, then you're going to get the perceptron. Okay? So this idea of a neuron kind of combines all these algorithms all together. This is not how I think these things were developed over time in the history of neural networks, but I like presenting it this way because you can see that using or thinking about neurons, we can design different algorithms. And this idea of a neuron, or of an artificial neuron, which normally we just call it a neuron for short, actually has an inspiration on the biological neurons. Biological neurons have synapses, they have activations as well. So this idea comes from biological neurons. So it's not just a nice visual way to combine these algorithms. But I don't want to talk much about this biological inspiration. So now I want to discuss how these algorithms, or how these individual neurons would perform on non-linearly separable problems. So we're going to consider this simple function f of x1 and x2 equal to x1, XOR x2, right? And we talked about this in the first lecture, I guess. But here's the truth table of XOR. Right? So here's the x1 value. This is a binary variable, so we can have either false or true values. Right? The same for x2 is also a binary variable, 0 and 1, false and true. So the XOR truth table returns 1 only when x1 and x2 have different values, right? So if you look at here, x1 is equal to 1 and x2 is equal to 0. And here you have x1 equal to 0 and x2 equal to 1. And we can plot this function like this. Okay? So if you try to build a neuron or a single neuron to solve this problem, the best you can do is something like this line here. You would learn a line that separates the space, and this line would get these two right, because these are below the line and they are 0 or -1. Okay? Then you're going to get this one wrong. And this one will be right, because this is above the line, so it's 1. So the best you can do would make at least one mistake or misclassification. You cannot do better than that. But what you could do is design or create another neuron that learns the not and function, which is linearly separable, and is this line here. Okay? And you could do the same to learn the OR function, which is represented by this line here, and is also linearly separable. But then, if you combine now the outputs of these two previous neurons with a third neuron that learns the AND function, which is also linearly separable, then you could solve this problem correctly with 100% accuracy. Okay? And that's the intuition behind neural networks. The idea here is that we want to learn new representations to the original problem. So the original problem gives us input X, but we want to learn new representations A that we call latent representations, because they are learned representations. So I'm talking about these new inputs now. If you think about this A1 and A2, this is an input vector to the final neuron. So we are transforming the original input to get these latent representations that hopefully will be linearly separable. And then you can actually make the problem much easier at the end here, and then we would be able to solve a problem that originally wasn't linearly separable, but after these transformations, we turned it into a linearly separable problem. That's the hope. We cannot guarantee that with real-world problems, because they don't have this nice, we won't get this nice interpretation when you train large neural networks on real-world problems. But when you are designing your neural network and you are experimenting with it, your hope is that this would happen. And there is ways to, there's metrics that we use to kind of understand how hard is the problem or not. Okay. Any questions? So we organize, or we give specific names to the structure, to certain parts of this neural network. First of all, we say that a neural networks is organized in layers. So the first layer is called the input layer, and even though it's a layer, it doesn't have any trainable weights associated with it. It's just the input. The hidden layer is any layer that is in between the input layer and the output layer. We can have more than one hidden layer if you want. And the output layer is the final layer of your network that gives you a prediction that can be either can be applied to a regression problem, to a classification problem, binary or multi-class. Okay. And each neuron here looks like that neuron we just saw. But in the context of multi-layer perceptrons, we normally use this A notation for intermediate outputs. And I'm going to use the Y hat notation only for the final layer or for the output layer. Because normally we use Y hat for the prediction. And A here is the output of any intermediate neuron in any hidden layer. So, okay. Now let's see how a multi-layer perceptron or MLP can compute outputs. We call this process the forward pass. As you will see, when you're training a neural network, we have two steps. The forward pass, and then there is a backward pass, which we do to compute the gradients that we need to update the weights of the neural network. We're going to train this model or any MLP or any neural network from now on using gradient descent. So this means that regardless of the architecture we use, we're going to need a loss function and compute the gradients. Okay. So first of all, let's slowly see how we compute the outputs of a two-layer. We call this a two-layer neural network because normally we don't count the input layer when you are saying the number of layers in a neural network. We just say this is a two-layer neural network, even though there is an input layer that we don't consider. And the first layer here has two neurons, or the first hidden layer, which is the only one, has two neurons, and the output layer has only one neuron. So this is the architecture we're going to see at this point. Okay, we can have more neurons on the hidden layer and more neurons on the output layer and more neurons on the input layer if you want. But for now, let's keep this simple example. So I want to formalize how to compute A1 and A2. Okay, and A1 here, what is A1? Now X1 and X2 they are actually dimensions of that vector X. So A1 would be G, right, of W1 X1, this is times, plus W2 X2 plus B, okay? I'm multiplying this input by this weight and this input by this weight to get A1. And notice that there is a second subscript there which we're going to use in each weight that we're going to use to denote the ID of the neuron. And the first subscript is just to refer to which input index this, or each input dimension this weight is associated to. Okay. So this would give us A1. And here I'm going to also put a 1 here because this is the bias term of the first neuron. Okay. And A2 is going to be similar. Okay. Now A2 is equal to X1, but X1 times W12, or W12 times X1 plus W22 X2 plus B2. This is the A. We can call this an A vector. And now we can use matrix operations to make these calculations more compact. And we're going to do that by separating these weights in a matrix. W11, W21, W12, and W22. Okay, so I just took these 4 weights out and put them here. And I did that because I can represent the same operation here by this matrix vector multiplication. Right? W11 times x1 plus W21 times x2. This is the first row of the matrix, of the resulting matrix, right? And here we would have W12 times x1 plus W22 times x2. Okay, so this, I combine this 2 computations in one vector matrix or matrix vector multiplication. Again, we need to sum B1 and B2 here, which also we put into a vector, so we can finally say that the vector A, which is our activations of the hidden layer there, can be written as G of W times the vector X plus the vector B. And this weight matrix stores all the weights of a given layer. And we are calling the hidden layer here layer 1. So what you're going to do is, here I'm going to say W squared brackets 1 superscript to denote that this weight matrix is the weight matrix of the layer 1. But now this is the computations of the entire hidden layer, or layer 1. This single computation computes both activations, A1 and A2. Okay. We're going to have to compute now y hat, which is the output of our final layer, which in this case is an output layer, right? So what is y hat here? Y hat is equal to G of this neuron now, okay? W1, A1 plus W2, A2 plus B1. But now this bias term is of layer 2, and we only have one neuron in this layer, right? So all of them are going to have, all the weights here are going to have 1 on the right subscript. Again, remember that the second subscript here refers to the neuron ID. And I only have one neuron here, so it's 1 for all of them. But I'm keeping this notation because then it generalizes well to any number of neurons you want. our weights also now refer to the weights of the second layer. Okay? And I can do the same, I can apply the same idea here of transforming these operations using matrix multiplications by doing this. Right now we have a row vector 1, 1, 2, and W 2, 1, 2. And this is just a row vector, or a row matrix, sorry, which is a vector, but we can think of this as a row matrix. And the activations can be written in a column matrix or a column vector like this, and then we can sum again B1, 1, 2. Because this multiplication here is going to give to us a number, one single number, right? We're going to do, which is this number here. It's a scalar, right? By the definition of dot product. This is a simple dot product written as matrix multiplication. And then our y hat finally can be written the same way we wrote our hidden layer. This is our layer 2. So they have the same, exactly the same calculations with different weights. Also here we can denote G of layer 1, and we can also use G of layer 2 because they can be two different activation functions. So yeah, here on the slides I have the same math. Any questions? So here's how we're going to do the forward pass for an entire data set. Okay? Remember, we want to do these calculations using matrices and vectors as much as possible because we're going to be dealing with very large data sets and large neural networks, so we don't want to use like for loops in our code. And if you want to, now we have a whole data set which is called capital X, and each example in this data set is in the columns. Okay? So the first column there is the example 1. And each row represents the dimensions of this example. So this is a problem where each example has 2 features. Okay? That's why there's 2 rows in that matrix. And we have m examples. As usual, this m letter is reserved for the number of examples in the data set. Okay? So I'm going to write it here. Now we're going to do this for the entire data set. I'm calling X, but we could call it D as well. And again, X now has this structure of X1 is the first feature of the first example. And then we have the second example here, X superscript 2, and the subscript denotes the first input feature, and this goes until m. All right. So we can apply the same idea here. I have a weight matrix W, which is equal to W11, 1, W21, 1, W12, 1, and W22, 1. Okay, and our B vector is going to be equal to B1 of the first layer and B2 of the second layer. Okay? And pay attention here that for the weight matrices, the number of rows, they refer to the number of neurons that we have. And we could have more neurons. If there were more neurons here, we would have a W1, 3 here, and W2, 3 here. Okay? Just to be clear. I could have as many neurons as I want. I just want to keep it simple because we can do this by hand. And then later on we can just deal with matrix notation. But it's important to do this once. Okay. So now we can write our activation 1 as G1 of W1 X plus B1. And this activation function, this activation matrix is going to look like this. A1, 1, A2, 1. A1, 2, A2, 2. All the way to the nth example, A of m. So remember, I have two activations per example. So each example I is going to give me a pair of A's. So here I have example 1, example 2 activation, example m activation. So I'm processing the whole data set at once. Which obviously we won't be able to do in a very, very large data set regime. Like when you're dealing with images, we won't be able to do this at once. But we're going to try to do as many examples as possible at once. And we're going to see how to do that later in this course. But if you're dealing with small data sets, we can actually process the whole and all the examples at once. If all of this fits in your memory and your CPU can actually do these operations, then you're going to do that in very few cycles. So here is the final, the computation we are doing on the board. And at the very final layer, I would have the same computation, but now with W2 and B2. Okay, and remember, B2 here is just a float because we have only one neuron. Remember, for the vector V, the number of rows is the number of neurons. The same for the weight matrix. Okay, the number of rows is the number of neurons. Here is the same as well. Here I only have one neuron, so I have one row in my matrix. Same for B. And then at the end, what is cool here is that at the very end of the network, at the output layer, is going to give you a vector where each dimension is a prediction for each example in your original data set. So you're going to do all the predictions at once. Okay? One y per example, x. Is this clear? Let's move on. So as usual, we talk about hypothesis space every I'm not going to say this enough, but every machine learning model has a hypothesis space, and so do neural networks. Now, this is a more compact notation or diagram where I'm showing here as an input the entire data set that goes through one hidden layer with two neurons and this layer has these two set of parameters, a matrix W1 and a bias vector B1. And then this layer outputs an activation matrix, A1, that goes as input to the output layer, or layer 2 in this case, which also has its own set of weights W2 and B2. And at the end, we're going to get y hat vector or matrix as output. It's a vector, essentially. But we can now write this computations that this neural network is doing. And this is specifically for a two-layer neural network. We can write it that way, right? We can have an intermediate matrix Z1 that is going to store the linear parts of the first layer. And then Z1 is equal to W1x plus B1. Now we're going to call the activation function. We're going to call the activation function G on the Z1 matrix to get the activation 1. It's nice to separate the computation this way. So we have the linear part stored as Z and the non-linear part stored in G. And the activation matrix is going to be a result of the G function being applied to Z1. And the same for any following layer. The difference is that the very final layer is going to give a prediction, y hat. Okay? And notice that A1 matrix becomes an input to the second layer that multiplies it by W2 and then sums with B2, gets Z2, and then you apply a new activation function to get the predictions. Okay? And this is our hypothesis space for these two-layer neural networks. All the functions that we can learn are represented by this formulation. From the final equation, from the last fourth equation here, I'm expanding Z2, right? And Z2 is equal to W2A1 plus B2. So W2 is here, and then I expand A1 again. And this is the expansion of A1. A1 is G of Z1, but G of Z1 is the same as G of W1x plus B1. So that's what you see here, plus B2 with this B2. So I just expanded this y hat here, and y hat is equal to age of x, okay? And I'm calling now this expression here, G of W1 times x plus B1 as edge of 1x, okay? Or in other words, I'm calling this as the kind of the hypothesis of the first layer. And I'm doing this so you can visually see that this is a function. So what we have in this as a hypothesis space for neural networks is a space of composite functions. So now we can learn to compose functions to solve non-linearly separable problems. So in other words, we are learning functions of the form f or g of f of x, okay? So our hypothesis now looks like this, g of f of x, where each composition is a layer. If I had 3 layers, I could have g of edge of f of x. So each composition here is defined by a layer. So you can put as many layers as you want to a neural network, and you're going to compose as many of these functions as you want. And this hopefully gives an idea of how neural networks can represent a wide range of functions. Okay. Okay. So, okay, speaking of activation functions, here are a couple of common functions we use. So far we've been using logistic regression because that's the algorithm we saw last lecture. And that's how that activation looks like. It's that S-shaped function that intercepts the y-axis at 0.5. And it tends to 0 when z goes to minus infinity, and it tends to 1 when z goes to plus infinity. Okay? That's the definition. G of z equals to 1 over 1 plus e to the minus z. And you can see here I already put the derivatives of that, or that's the slope or the derivative of this function. Okay. Another common activation function that looks a lot like a sigmoid because it also has this S-shape, but it's shifted a little bit on the y-axis, is the hyperbolic tangent function that now it tends to minus 1 as z goes to minus infinity, and plus 1 again when z tends to plus infinity. But here is a weird one, which actually is the mostly used right now. And this is called the ReLU activation function, or rectified linear unit, which is weird because it's non-differentiable at one point, which is when z equal to 0. It's not continuous at that point. Even though it's not continuous, it's perhaps one of the most used activation functions these days. And it became popular, at least as far as I know, with the AlexNet paper. They use these activation functions as part of their convolutional neural network and showed that using this helps flowing the gradients. We're going to see this, that one of the major problems of deep learning is as you grow your neural network in size or in depth, we call it depth, or the more layers you have, the more depth you have, the harder it is to train these models. And it's hard to train because numerically speaking, it's very hard to compute the gradients. Essentially, they tend to explode to really big numbers or shrink down to numbers that are very, very close to 0. Because we have to compute these derivatives, and the more layers you have, you're going to have to do, intuitively you're going to run a lot of multiplications of small numbers or multiplications of very large numbers. And then we have these behaviors of, like, we call it vanishing gradients or exploding gradients. And this happens in this, whenever you try to have this, it normally happens when you have big networks. So this idea was introduced to deal with that problem. Okay? And one intuition about it is that, first of all, it's interesting that when z is negative, the ReLU returns 0. And then when z is positive, this is just a linear function, or the identity function. Basically, it's defined as g of z equals of max of 0 between 0 and z. So it pretty much just takes the number, returns the same number if it's positive or 0 otherwise. So here's the derivatives are very simple. That's the one interesting idea of this function. The derivatives here, they don't involve any multiplications. Here is a different one that is similar, that takes the ReLU function. It's called leaky ReLU because it has this tail here. So what it does is it's defined as the max between 0.01 times z and z. So basically what it does is it is a linear function when z is negative, but with this very small slope. Okay? And it keeps the same when z is positive. And here are the derivatives. There is variations of ReLU. There is other activation functions. This is just a common activation functions we use when designing neural networks. Right now, keep in mind, ReLU is the mostly common one for hidden layers. We're going to see that for the output layers, it really depends on the problem. Any questions? All right, so here's an important idea. Why do we need nonlinear activation functions? So here is our hypothesis space written as a single equation times G of W1 times X, this is a vector, plus B, this is a vector, 1, plus B2. This is just a number for this example here. Okay, so this edge of X function, or this equation I wrote on the board, is the hypothesis space for this network we see on the slide. And what I'm trying to say is that these functions here, they have to be nonlinear. And the reason is, if they were linear, and imagine for the sake of the argument that these were just the identity functions. So then we could just get rid of these, and that would be, gives us this expression, W2 times W1 times X plus B1 plus B2. And now I can distribute this, and now I can actually put a parenthesis here and call these W prime X plus B prime. I'm calling this expression W prime and this expression B prime. Essentially what happens is, if they are linear, your entire neural network will be a linear model. So it doesn't matter. You're not going to learn any more complicated decision boundary than a linear function. We're just going to use more weights for that. But at the end, it's going to be a linear function. So you need to add these nonlinear activation functions to learn nonlinear functions. Okay? And that's what I was trying to claim here on the slides. So it's important. So in the other words, if you just pick linear activation functions, you are not doing any better than a logistic regression at the end of the day. Oh, another important detail of neural networks is how to initialize their weights. And in logistic regression and linear regression, we could initialize them with zeros. And in fact, I think we did that in the code. I think in the programming assignment, that's what I tell you to do. So normally you have a W vector like this, and then you start it with zeros, and you have a B and you start it with 0. We do that in linear regression. They're all the same values. And we can do that in linear regression and logistic regression because in there we have a convex optimization problem. And no matter where we start, we could start at any point here. If this is W, I can pick a W equal to 0 here. And I can start here, and then I can go down. I could start at 1. I could start at minus 100. I could start anywhere. and then gradient descent would take me down. Okay. But in neural networks, we cannot do that. Instead, what we do is we initialize the weights of the entire network. And when I say initialize the weights, now I have a weight matrix per layer, right? So I'm going to initialize these weight matrices with random numbers close to 0. Okay? So very small numbers, but they're not the same. And the intuition is, if we did initialize all of them with zeros, and here's an example. This is our network that we've been using the entire lecture. This network would have this set of weights, right? And also there should be a B2 here, which was just a number. But W1, B1, W2, B2. If I use the same set of weights, then the green neuron, the blue neuron, they'll be the same. Because they will do exactly the same computation. Right? That's what I'm showing here. The activation of the first neuron is going to be exactly the same as the activation of the second neuron. And then when I compute the gradients will be the same. So when I update the weights, the updated weights will be exactly the same as well. So what's going to happen is you're going to end up learning 2 different neurons, but that do the same computation. Okay, so we don't want to do that. That would be a waste of compute, right? And also would limit our model. So in other words, what we do is just we start with random weights. But it's the idea of initializing it close to 0 comes from the gradient. Just intuitively, let's consider that the logistic function as an activation function. Let me draw this here on the board. Something like this. This is 0. So imagine this is W. Okay? This is actually Z, right? But this is Z equals to WX plus B. So if W is close to 0 and B is close to 0, Z is going to be close to 0. And why do we want it to be close to 0? Because around 0, the gradient or the slope of this function is the steepest. So right here, the slope is very small. And right here, also the slope is very small. But here, it's very steep. Because this function here is kind of exponential around 0. So by having this very steep gradient, I'm going to learn faster. Because when I take a step, when I take a step at gradient descent, this step is going to be bigger. Okay? If I started my weights here, this step would be very small. Okay? So that's, in practice, how we initialize neural networks. There's even more fancy algorithms that try to calculate some more, instead of using just simply random weights. So there is one algorithm, for example, called Xavier initialization. There is people studying how to initialize weights of neural networks to get better performance in training time. Okay, it's not a simple like aspect of neural networks. It's actually a very important one. And also, I don't have it here, but remember that in neural networks, we are not guaranteed that our optimization is going to be convex. Okay? And we're going to assume that it's not convex. So depending on where you start on your loss function, or depending on how you initialize your parameters, your gradient, you might have higher chance of getting to the global minimum than in other places. So depending on where you start, you might get stuck in local minima or not. Okay? So initializing parameters is actually a very important aspect of neural networks. Okay, I'm almost done. So here is just, now I think we have less math towards the end, but just some nomenclature, some vocabulary here. So we've been talking about neural networks and multilayer perceptron. Nowadays, we don't even say this name as much, multilayer perceptron. That name has been more now popularly known as feed-forward networks or fully connected neural networks. I think feed-forward networks is a more general term that even considers other architectures, but this idea of multilayer perceptrons, where each neuron is connected to every other neuron, so they are all connected to each other in this layer structure. This was originally defined as a multilayer perceptron because it was this idea of combining multiple perceptrons, but nowadays people call it mostly fully connected neural network. Maybe they want to get rid of the perceptron name or something. But here's some vocabulary. So when you have a single neuron, we call that a neural network with one layer, and we say it's shallow. And here we could see, for example, logistic or linear regression models as being in this category. And then if you add a hidden layer, which is the kind of models we've been dealing in this lecture, right? We're going to have a neural network with two layers, for example, right? Remember, we count only the hidden and the output layer. We don't count the input layer. So here's also what we call a shallow network. And we can keep growing, right? Here we have a 3-layer network that has 2 hidden layers. And the output layer also has one neuron at the end. And here is a deeper neural network with 6 layers, 5 hidden layers, 1 output layer. Okay, so there is not a formal number that defines when the neural network starts to get deep, but in practice, historically at least, MLPs, they have been studied in this range of just one hidden layer. So whenever you have something like with 4, 5, 6 hidden layers, then we start to thinking as a deep neural network. Okay, and here it's important to highlight that you can pick the number of neurons that you want for each hidden layer independently. It doesn't really matter. You can pick the first. Sorry about that. It matters for the training. It matters for your problem, but you can pick different numbers for each layer here, as I show in the diagram. And they don't have to like decrease in depth, like I'm showing, but it's also common. It's a common way of organizing networks. Okay, so here is just a general formulation of multilayer perceptrons with L or uppercase L layers. So our first layer there has a linear part W1x plus B1, right? And then we're going to have an activation A1. And then we have Z2, A2, right? All the way down to ZL. And then at the very end, we have a prediction, right, with the output layer L. We can rewrite this in a more general formulation using Z of L lowercase is equals to WL times A L minus 1. In other words, the current layer L takes as input the activation of the previous layer. Okay, that's why L minus 1. And then the activation of L is equals to G of ZL. And in a vectorized form, you would get it this way. Okay, this is just for a single example. and this is for the whole data set. One important thing is, I think this starts to answering the questions we got before, which was about when and how do you use multiple neurons in the output layer. So when you're designing neural networks, the size of your input layer and the size of your output layer, they are defined by the problem. So the size of the input layer is just the number of features you have. So if your data set has 3 or 4 input features, that's going to be the size of your input layer. Right? For example, in the previous example, we had age and tumor size. So the input layer would have 2 neurons. Right? And we were dealing with binary classification, so it's either 0 or 1. In this case, I only need 1 neuron in the output layer. So the problem itself is defining the size of the first and the last layer. Okay? And specifically, if you're dealing with regression problems, you're going to have only a single neuron as an output, because you want to output a number. Okay? And if you're doing binary classification, the same. If you're doing binary classification, you want to predict, or you can think of it as a probability, like logistic regression. You're going to give a probability value as an output. And so we're going to use only 1 single neuron. And also, the problem kind of defines the activation function you're going to use at the output layer. So in your hidden layers, you can pick any nonlinear activation function you want, and the most common one these days is the ReLU function. But at the output layer, the activation function you choose really depends on the problem. So if you're doing regression, you normally would want just the identity function. You would get the number that is the output of the layer, and just that's your prediction. But if you're doing binary classification, you're going to get the output and just pass it through a sigmoid activation function to get a probability. So in other words, yeah, the last layer is very attached to the kind of problem you have. Which is an interesting idea, because it's kind of like a building block, right? If you have regression, you're going to use identity. If you have binary classification, you're going to use or logistic function. For multilayer, for multi-class classification problems, for example, the handwritten digit classification, where you have 10 classes, then you're going to need 10 neurons in your output layer, because you have 10 labels. If you had 100 labels, you would have 100 neurons. ImageNet had 1,000 classes for millions of images. So the AlexNet paper, that paper, if you check the architecture, the output layer has 1,000 neurons, because they have to predict 1,000 classes. Okay? And attached to that structure, you're going to have the softmax activation function. So if you're dealing with multi-class classification problems, we're going to use this activation function at the very end, at the very last layer. And it's defined this way. It's g of z equal to e to the z over the sum of from j equals 1 to c, where c is your label space. Remember, this is the summation of your z value per class you have. So I think this is the best to understand this as with an example. Imagine you have your activation function. So your activation, the linear, remember z is the letter I use for the linear part of the layer 2 here. So imagine if I had 5, 2, and minus 1. Okay? So if I had this, then I would compute the softmax of my last layer by first computing this vector e to the z, which would be e to the 5, e to the 2, and e to the minus 1 because of these results here, right? And that would be summed by, divided by the sum of these 3 numbers. So just sum e to the 5 plus e to the 2 plus e to the minus 1, you would get this number here, 156.70. What this would do in practice is it would transform your linear part into a probability distribution. So if you look at this W hat I here now, so it's 3 elements summed to 1. So this defines a probability distribution. And when you're doing multi-class classification, your prediction would be the value or the class here that has the maximum argument. So for instance, here I would predict class 0 because it has 52% chance. Okay, so I would just pick the class that has maximum probability. Okay. So we've seen this before, so I'm not going to worry too much. In previous lecture, we introduced binary cross-entropy as a loss function for binary classification problems. And here is the definition we created. We actually developed last class, right? And here's an example if you want to review this idea. So when you're dealing with multi-class classification problems, we have to use another variation of binary cross-entropy, which is actually a more general version, which is called categorical cross-entropy, which pretty much is a cross-entropy for more than 2 classes. So now I have an extra summation here from C going from 1 to capital C, which is the number of classes you have. Okay? So here I want to actually show an example. Imagine I have these true labels, and here, this is important. Consider that I have a multi-class problem with 3 classes. So I'm trying to say there is that there is an example at W2 that that has label, this is label 1, this is label 2, and this is label 3. So this is the ground truth distribution of this example. It has label 2, so it means, in other words, that it has probability of 1 of being of class of label 2, and probability 0 of being from label 1, and probability 0 of being from label 3. Okay? And my predictions are y hat 0.1, 0.7, and 0.2. So what the categorical cross-entropy does is it compares this value with this value, this value with this value, this value with this value. Okay? So it forces your model, when you're running gradient descent, it forces your model to approximate your prediction to this real ground truth. So you want this value to be as close as 0 to possible, this one to be as close to 1 as possible, and this one to be as close as 0 as possible. And this loss function computes exactly that. Okay? And that's it. So, sorry for running a little late, as I think usual, but you're going to get better, I promise. Thank you very much. See you next Wednesday.